excited to introduce Hannah, who's going to talk to us about remote sensing opportunities.
Yeah, I'm Hannah Dietterich. I'm up the hill at the USGS Alaska Volcano Observatory, and we're going to talk about the remote sensing data that we use here and what's out there for cool observations. And this is really looking at the ground above volcanoes and the atmosphere above volcanoes, the ground of volcanoes, to look for signs of unrest and also eruptions, eruption style dynamics, things like that. This work? Nope.
I think just click on it with the remote, the mouse. Use the mouse.
With the mouse.
And then just click on it, and then you should be able to do anything you want.
Yeah, okay. Here's the silly USGS cartoon about how we monitor volcanoes. And we're gonna go into this corner up here. Looking at remote sensing is fundamentally just imaging, but from a few different platforms. So we work a lot with space-based imaging here because we're covering a very large area, but we also use aerial remote sensing, and of course a lot of ground-based remote sensing has been mentioned too. And we can use a lot of different wavelengths of light to look at different things. So of course we can see what's happening in a volcano with our eyes with visible light, but we can go into the UV to look for sulfur dioxide emissions, for instance. We can go into the infrared, look for ash, look for warm things, hot things. And then we already talked about a little bit there INSAR, that's into the microwave territory, and then all the way out into even longer wavelengths to detect lightning or sort of Doppler radar looking at particles. So we can observe a lot of things about volcanoes with a lot of different techniques. So are those chats important? Yeah. Okay. The thing saying we can't see or hear. So when we're looking from further away, we might have a lower resolution view of our volcano, and then we can use a variety of different wavelengths of light to observe everything from gas coming out to like the dome in Cleveland volcano to the ash cloud erupting from readout, say. And so at AVO, we do a lot of operational remote sensing. We're looking for long-term like establishment of background activity and then detecting change from it at all our volcanoes across Alaska. A nice example from a couple years ago is at Kanaga volcano, the top split open. I guess actually happened twice now. So looking for changes at all of our volcanoes. When we do detect unrest, we look a little more closely for what's going on or low-level eruption activity. Oh wait, I want this. And then when we actually have an eruption underway or expected, so this is an example from Shishaldin, we're trying to monitor in real time what's happening, what's coming out, where's the ash going. So we have a 24/7 on-call duty remote sensing scientist role who is making observations every day. And so we mentioned GeoDiva earlier, part of GeoDiva. Ooh.
You've been interfered.
Sorry, Hannah, online folks aren't seeing the slides.
See, the chat seemed important.
Your instincts were right.
You don't want to suddenly see a bunch of chats when you start talking. Or you have like, something in your teeth. The daily remote sensing check is what populates the AVO remote sensing database, and this is really just a qualitative summary of time series data. So looking for things that are hot, each of these icons, A is ash, H2O is steam, all the like colored little hexagons are different, like it's really hot or just a little bit hot or things like that. So we do this every day for all of our volcanoes using a bunch of the sort of data we check daily. We also get alerts. These were demonstrated for like our RSAM and infrasound alarms. We also get alerts for things like lightning or for ash cloud detections from the NOAA Volcat system. And then of course, during eruptions, doing observations during response from webcams, from real-time satellite imagery, from radar. So we use some sort of in-house tools for this. Our VolcView website and AshCam websites are public. These are our satellite and webcam data viewers. And they don't store data indefinitely. I guess Ashcam now has an archive, but that's what we use in our daily checks. And then these matter most alerts of new data coming in or new observations. And really what we're looking for is in the lead up to an eruption, we might have ground deformation start to happen. We might see melting of snow or ice, or say the formation of a new crater lake on top of spur. We might start to see gas coming out of a volcano prior to eruption, or the surface warming, fumaroles heating up and generating hotspots that we can detect from satellite. And then when an eruption is underway, we're looking for what's coming out. Ash clouds, how high they are, where are they going, how long they're lasting, lahars, lava flows, all those sorts of hazards, and how they're evolving in time. So we can use remote sensing to look at all these. This is the cartoon from Matt Pritchard. Here's just an example from the Great Sicket activity in 2021. It's already been mentioned a couple times. For years before we had seismic activity, but in the months beforehand, we started to see warm surface temperatures. The upper plot is volcanic radiative power, which is just like how much heat's coming off. The yellow, orange, and red dots are our qualitative measurements. The other dots are the quantitative tracking of heat of emissions. And at the same time, closer to the lead up, we started to see SO2. The volcano exploded, and then when it began to erupt lava flows, our first detection was in satellite radar imagery, showing a new pimple forming on the surface that was a lava flow. And then as the weather cleared, suddenly it was like, okay, now it's really hot, so lava's coming out. In the satellite world, we're really, that bar says polar orbiting, but geostationary satellite data, this is satellites that are really far away from Earth and are just looking at this, like orbiting at the same rate the Earth is rotating. So they're basically recording a video of what's happening on the surface, but really coarse resolution. And then we have a bajillion other satellites in polar or inclined orbits that are in lower Earth orbit, like going round and around while the Earth spins underneath them. And they're able to make fewer observations, but at higher resolution. So we mostly use a lot of meteorological satellite data. That's all operated by NOAA. So our GOES satellites, VIIRS sensors, things like that. Because we go all the way west, we also use the Japanese satellite Himawari to observe eruptions in the Western Aleutians. There's a lot of public satellite data. USGS operates Landsat, European Space Agency operates Sentinel constellations. We use all of those. We use a lot of radar satellites, that's already been mentioned. And then we use a lot of commercial satellite data. And these offer really very high resolution looks that we have access to through our US government contracts. And that is harder data to share. But what we can do is we can detect hotspots. That long arrow is pointing to really bright pixels on top of Shishaldin. We can then task a higher resolution satellite to take pictures of the top of Shishaldin, and we can see that, hey, that hotspot's actually like an eruption. There's a lava flow going off to the north. This is like an ashy steam cloud during an eruption. And we can pick out a lot more detail. We can measure the channel width of the lava flow and how long it is and all these other features. We can detect changes in thermal emissions through time. So this is the summit of spur warming up. I guess there's a little animation of that using nighttime Landsat imagery in the thermal infrared. So the formation of that lake and the fumaroles heating up on top of spur over the past year or so. When a satellite passes overhead, it can take more than one picture. So with optical data, so visible light, we can use 2 passes and stereophotogrammetry to try and reconstruct the surface, the ground surface. This doesn't work where there's steam, which is the hole in the center of the Great Sicket lava flow, but we can do things like track the eruptive volume through time. And of course, there's lots of surface features and other morphology of the surface that can tell you a lot about the dynamics of the eruption, and in this case, also the ice just outside of the lava flow. And then SAR already got a shout out. Of course, you can use synthetic aperture radar satellite images. If you have more than one pass, you can interfere those and get nice pictures of aniac check deformation. But SAR also has the property of being able to see at night and through clouds. And so we use it a lot just for imaging. And in this case, I told you that we detected the Great Sitkin lava flow initially with radar data, and that's the little pimple that appears inside of the crater. And then of course, the lava flow spills out of the crater and then even spills out of the summit crater and down the flanks. So we use this to be able to, of course, make measurements, but also track activity at night and when it's cloudy, which it is here often. But sometimes we want to see the clouds. And so you can use thermal infrared wavelengths of light to detect things like ash separate from weather clouds. This is older AVHRR data. We can also use satellite UV to map. This is like the coolest SO2 plume from one of the like spiraling away from Shishaldin in 2023, detected with Tropomi, which is on the Sentinel platform. And then we can do things like measure cloud heights using the temperature of the cloud. So the thermal infrared measurement and comparing it to atmospheric soundings or weather models for like how high up that cloud has to be to match the atmospheric temperature. And so that's really important during eruptions. During eruptions, we want to look at that more real-time data. The GOES satellite out most places takes pictures every 10 minutes. Here over Anchorage, we can get pictures every 1 minute because it's often targeting here. And we can access that data. That data is on Amazon Web Services, I guess within about 1 or 2 minute latency. So it's near real-time data. And this allows us to, and during a Shishaldin eruption, we see this hot spot of the volcano in a green plume away. That's a gas and steam plume. And then eventually that's going to turn bright red. That's the ash plume. So we can detect what's coming out of the volcano, characterize it, and then do that quantitatively in time series too. So looking at the heat coming out of the volcano, in this case, there was a lava flow and a high lava fountain that started. That high lava fountain was producing that steam plume and putting out a bunch of SO2. And at some point that transitions, the plume heights in the middle there, transitions to a lower ash cloud. So the plume height dropped when it began erupting ash, and the RSAM disappeared even though ash was coming out of the volcano. So this is work by one of our NSF interns who's been up here, Andy Gomez-Patron. When we can get to our volcanoes, which happens less, we can use airborne remote sensing data. So this is imagery from a helicopter, from a fixed wing aircraft. We don't do a lot of drones in Alaska, but it's happened. And so last Friday, we did an overflight of Mount Spur with gas instrumentation. And then one of the things we're doing when we're there too is taking both infrared and normal visible photos from many angles around the surface to reconstruct a 3D model of what the summit of Spur looks like. We can measure the volume change. We can measure how the lake level's changing, how the lake is growing, things like this. So at the bottom here, there's a comparison between overflights like a month apart and what's changed. Really just snow and ice is falling into the lake. Sort of interesting. And then we can measure the temperature of the fumaroles with infrared cameras. And then sometimes we can get the Coast Guard to go fly over volcanoes.
Yeah.
And then, so in this case, Pavel had seen in his daily duty check that Shishaldin had gotten hot suddenly. So it's like, well, it's probably erupting, maybe. But we were on stuck at the Dutch Harbor Airport, and the Coast Guard was leaving, and I was like, well, you guys should go fly over that. Which maybe since it exploded like 2 days later wasn't the best advice, but like they sent a video. I was like, okay, yes, that's erupting. And then, of course, we can, at the ground, we can also take photos from the ground. So we already talked about our massive webcam network. We have, in this case, at Shishaldin, 3 views of the same volcano from AVO cameras. The purple lines are also cameras that the FAA operates for aircraft. And those give you a larger view, but that sometimes when there's big ash clouds, that larger view is what you want. And in this case, this loop is showing both a summit plume, but also like another plume going down the flank, and that's the front of a lava flow advancing as it's interacting with the ice. Other ground-based instruments that we have access to, this is the USGS radar that got taken away last week. But the FAA also operates radar in Cook Inlet, not anywhere else in Alaska, and Doppler radar, which of course everyone's used to seeing for like checking whether it's going to rain on you at 49th State last night, or or just looking at cloud and rainfall forecasts. You can also see ash clouds. And sort of the reflectivity, so you can see things about the grain size or ice and things in ash clouds in the process. And then finally, global lightning networks. There is a satellite lightning center on GOES. It doesn't see spur, it sees some of the southern Aleutians, and that's looking for bright flashes. But there's also a ground-based lightning monitoring network, and there are instruments in the Aleutians that we use because natural thunderstorms are not common in the Aleutians. And so lightning is a very good indicator of ash emissions. And so here's our like Boguslav lightning alerts going off when there's Boguslav eruptions. And here's just an analysis by another intern we had here last year, Rui Moda, looking at when lightning is occurring and where during the Shashaldan eruptions to understand both what's generating the lightning and also elements of the eruption dynamics. Ooh, okay, well, that's a good segue to talking about how to get data. Hopefully everyone saw Michelle's spaghetti chaos diagram. A lot of that data is various remote sensing. So for satellite data, AVO doesn't operate any satellites. Satellite data is all external to AVO. We bring in and process data that's available for viewing in bulk view. The Geodesy app also already got a shout out. Our SAR data goes into that. And then we use a lot of different partner tools from NOAA, the Volcat system, NASA operate various visual like ways to access, search, and view satellite imagery online. And a lot of that data is public. Most of what we use is NOAA meteorological satellite data, NASA, USGS, all of these different systems. There's in process a SAR super site for the North Pacific that's like coming soon as more companies sign on. You can bug Mike Poland about that. But we also use a lot of commercial satellite data. This is data, we get it through the National Geospatial Intelligence Agency. We cannot distribute the raw data that we receive through that license. NASA has a program called the Commercial Satellite Data Acquisition Program. You can task satellites through that system. You can also request data that we've already tasked that just exists. I don't know how hard it is. Like I've done it for a few things, and you just fill out a form online and someone says, okay. So this is like Maxar satellite data or Capella, ICEYE, high resolution radar, things like that. So there's a way to access it through NASA's system for academic use. For airborne data, we already heard about the AVO image database. If you want a video from the Coast Guard of Shashaldan erupting, that's on the image database. It will be on the multimedia database, and then you'll actually see the thumbnail instead of having to like risky click download it first. But it's searchable. You can search for oblique air photos of some target. It is not a long-term repository of every photo taken during an overflight. That's hundreds of photos. They're raw photos. We need a better system for that. But it's a way to see what we have. We also then, when we process orthoimagery or digital terrain models of the surface, so the example here is from Veniaminoff. We had an overflight during the eruption of Veniaminoff and after the eruption of Veniaminoff. We've processed those into elevation models, had them reviewed. We haven't really talked about the USGS data review process, but we made a USGS data release. And the best way actually to search and access data from that sort of thing is in the Alaska-Aleutian portal. Don't go to USGS for elevation data. It's a terrible website. But the state of Alaska operates a great one, and you can access an Arctic DEM, you can access the USGS 5-meter IFSAR, which is the best terrain data for Alaska. we don't get 1 meter data here, LiDAR isn't, and then our pre-erupt, our synterruptive and post-eruptive data can be downloaded and accessed there too. But we need better solutions for that kind of thing. And then ground-based data, you can see Ashcam online. You can watch our live stream of Spur on YouTube. All the archival webcam data is viewable through the Ashcam API. I have been instructed to tell you that bandwidth is limited. So if you are trying to download years of webcam data from somewhere, ask people rather than just like HTML slamming the server. Doppler radars and items on web services, lightning data, a lot of it's commercial, but there's a way to request access for research purposes that various people have been quite successful at. And then there's the time series data